Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. Plan for today is we're going to continue our discussion from last time of quadrilaterals. As far as office hours go, I've got my usual office hours today after class and from 2 to 3. Tomorrow at 10 and at 1. Tomorrow morning I have to cut my morning office hour 20 minutes short because of fall convocation. Got to get the cap and gown on and go line up. So everybody can go ooh and ah at how fancy all the faculty was or something. Quiz Friday on triangles. So the triangles packet specifically. And then don't forget, homework 5 will be due Monday. So a couple of announcements. First of all, those of you who are registering for classes, you may have noticed game theory filled up. If you're interested in taking game theory with me and you haven't signed up for the course yet, send me an email. I'll put you on the wait list and might be able to get you into the course and try to add in a few extra seats. I'll need to do some investigating on that front. But if you're interested, do that. Otherwise, most of the math classes are still there's lots of slots available. Any questions or comments before we get started for today? What did 0 say to the 8? Megan?
Nice belt.
Hey, nice belt. Okay, so when we left off last time, we had started talking about different quadrilaterals and various Hilbert planes. We said that a Sakari quadrilateral, ABCD, is one where the two base angles are right angles, and the two sides of the quadrilateral are congruent to each other. And we proved that in a Hilbert plane, at least, that the summit angles of the Sakari quadrilateral have to be congruent. Meaning, if the two base angles are right angles and these two sides are congruent, then this angle and this angle have to be congruent to each other as well. We said that in Euclidean geometry, the top two angles turn out to have to be right angles. It's going to turn out, though, to not necessarily be the case in a non-Euclidean model. So, for instance, we saw that if you construct a Sakari quadrilateral on spherical geometry, it turns out that the two summit angles, the angles up top, are going to be obtuse angles. And that in the Poincaré disk, which is sort of this new hyperbolic geometry model we looked at last time, turns out they're both going to be acute. So in any Hilbert plane, these two angles up top in a Sakari quadrilateral have to be congruent, but they don't necessarily have to be right angles, like they would be in Euclidean geometry. And I think that is where we left things off last time. Any questions or comments about that before we move on to the new stuff? Checking on my attendance. So, next up, I want to introduce a new type of quadrilateral, a Lamborgh Quadrilateral. And I meant to look this up for today, but I actually forgot. Quadrid, there's an R in there. Spell. I have to look this up to see if it was pronounced Lambert or Lambert or something. I'm going to go with Lambert for now. If I find out otherwise, I will let you know. A Lamborgh quadrilateral is one with at least 3 right angles. Meaning, if we were to try and draw one out, we'd have right angle here, right angle here, right angle here. Who knows for the 4th angle? But something like that we are going to call a Lambert quadrilateral. So, based on your hey, you look like you have something you want to ask.
Oh, well, I was just thinking in my head, if the
bottom two are always congruent, the top two are always congruent, how you can have a fourth that's not congruent to anything.
Well, I don't think we necessarily need that these top two have to be congruent. In a Sakari quadrilateral, they do.
Nice.
In a Lamborgh Quadrilateral, though, we have no guarantee we don't necessarily know that, say, the two sides are congruent to each other, the left and right sides. And so this theorem doesn't necessarily have to apply. If we knew that the left and right sides were congruent, then all Lamborgh quadrilaterals would also have to be Sakari, which would mean then by this theorem that since this top angle is a right angle, this one would have to be as well. Turns out, you can probably guess that it's not going to necessarily be the case that the two sides have to be congruent, and thus this angle doesn't, the fourth angle may or may not be a right angle. Okay, Elaine, without looking at your packet, can you think of a type of model of geometry where this fourth angle would probably also have to be a right angle?
Like regular, like R2.
Like in regular geometry? Have we defined that?
I already looked at the theorem on the page, so do you want me to tell you the answer or no?
How about in Euclidean geometry?
Yeah. I do want to cheat.
Actually, regular geometry is actually a thing we haven't defined yet.
Whoa.
Yeah. Jared?
Oh, I was just going to say R2 where all the points are dyadic.
Oh gosh, in dyadic geometry? Okay, I actually need to think about that one. Dyadic geometry, would the fourth angle have to be a right angle? Yes, it would.
Yeah.
Although, I'm trying to think, you run into an issue where the fourth, where these 3 points are all dyadic points, but this fourth point up here would not necessarily be a dyadic point. We were allowed to take this and if, for something like this, then yes, it would have to be, but if we were to rotate a little bit, I don't know. Thanks for giving me an idea for your final exam.
No more dyadic.
No more dyadic?
That was hard.
I think it would be fine.
Oh, Jared's doubling down on it. Okay, well,
Yeah.
and now,
Because...
I mean, I said that as a joke, but now.
Oh, no, I was talking about the point in the corner, but...
Okay, now you're giving me. Okay. Anyways, turns out in Euclidean geometry, this fourth angle is going to have to be a right angle. And so we have another theorem which says that in a Euclidean plane, it's going to turn out that not only every Lamborgh quadrilateral, but also every Sakari quadrilateral is a rectangle. Which basically says the missing angle has to be a right angle. So we're going to prove this for the case of the Lambert. Gosh, I'm already mixing up my pronunciations. Lambert quadrilateral, that if you have 3 right angles, the fourth angle also has to be a right angle. And then the Sakari proof is pretty similar. So let's start off. We're going to assume we have a Lambert quadrilateral. So we're going to assume that if these are our 3 points, A, B, C, D, we're going to assume that these 3 angles are right angles, and our goal is going to be to show then that at D here, we have a right angle. So first of all, we're going to start by saying, let E be the unique point on the line BD, not the line BD, sorry, the ray BD, So the ray is going upwards from B here in this diagram, such that angle CEB has 90 degrees. So in other words, we know that for some point on this ray here, going from B in the direction of D, there should be some point, which we'll call E, that makes it so that if we take the angle going from C to E to B, we get a right angle. How do we know that such a point E has to exist? And for that matter, that it's going to be unique? Luke?
Because the corollary, I can't remember the name of the proposition, but it's that where you have right angle, where you have, if two lines are both perpendicular to one line, that means that the first two lines are parallel to each other, and therefore if you have another line that is perpendicular to one and it intersects the other, it must.
So we have two lines that are both, so like AC and BD here are both perpendicular to AB and to CE. So basically we could use that to say something like AB and CE both have to be parallel. I don't think that guarantees, though, the existence of a point E necessarily. I think we actually have one of our axioms that has to hold true in any Hilbert plane that guarantees there exists a point on this ray that'll give you this right angle. Okay?
Is that congruence axiom 4?
It is indeed. Yeah. Congruence axiom 4, one that we haven't really used very much. We've seen congruence axiom 1 get used a lot, the one that says, given any line segment in a ray, there exists a unique point on that ray that makes the line segment congruent to the original one. That one we've seen used several times, but we haven't really seen congruence axiom 4 get used very much. Where if you recall, congruence axiom 4 is the one that says if you have an angle, and if you have a ray, like so, there exists sort of a unique way to have an angle that is congruent to the original one. So in this case, that's going to tell us there's a unique point on this ray that will create a right angle to this one, or an angle that's congruent to this angle, which if it's a right angle means we're going to get a right angle here. So we know that there has to exist a point E that's going to make a right angle with CE here. And then, here's the trick. We can say that, and here look, I think we're going to be applying our corollary that you mentioned earlier. We could say that by our corollary to the alternate interior angles theorem, since CE and AB are both perpendicular to BE, so we know that CE and AB are both going to meet up with BE here at right angles. What do we know about pairs of lines that meet up with the same thing at right angles? Well, if we're in a Euclidean plane at least, that's going to tell us if you're two lines that are perpendicular to the same thing, they have to be parallel to each other. Or they're the exact same line, but that's clearly not the case in this scenario. So CE is parallel to AB. They have no points in common. And now we can say that thus CD and CE, the segment here, the summit of our Lamborgh Quadrilateral, as well as this new segment, CE, that we constructed, CD and CE are both lines that pass through the point C and that are both parallel to the same thing, the line AB. So what do we know? We have two lines, both of which happen to pass through the same point and are parallel to this other line. And we're working in a Euclidean plane, meaning we have the Euclidean parallel postulate. So, Steph, assuming that we have the Euclidean parallel postulate, given this line here, AB, and a point up here, C, if we have two different lines that are, how many lines should there be, Steph, that both pass through the point C and that are parallel to AB?
In the Euclidean plane, only one.
Only one. There should only be one line that passes through C and is parallel to AB. That's right, found it. So, but we just found two lines, CD and CE, that both do that. So what does that tell us about CD and CE? Jack?
They're the same line.
Is that what you're going to say? Yeah. Thus, by the Euclidean parallel postulate, CD equals CE, and thus DSE equal to D. Yeah, Nick?
Why don't you have to show that CD is parallel to AB?
Good question. Why do we not have to show that we showed that CE has to be parallel to AB, but why didn't we do the same thing for CD? The problem is if CD and AB are not parallel, then we didn't have a quadrilateral to start with. We would have said, oh, then we have a scenario that looks something like this would have been our starting thing, and that's not a quadrilateral, that's actually just a triangle. So we can kind of assume that since we have a Lamborgh Quadrilateral that we have to work with, that CD and AB are not going to intersect. CE, though, it's a little bit unclear whether that's going to intersect AB or not, so that we had to prove can't happen. That's a good question, and something I kind of just glossed over, that CD and CE are both parallel to AB, and yeah. Yes, Jack?
And I think you could also say that CD and AB are both perpendicular to CA, so that they're have to be parallel to each other.
Ooh, that's a good point. Yeah, so basically, since we have a scenario where we have two lines that are both perpendicular to the same thing, yeah, they have to be parallel. That's probably a better way that's a good way to describe it, that it can't possibly be intersecting like this in a way that forms two right angles. Unless these were the same line to start with, in which case, oh, hey guys, check out my sick quadrilateral here. Oh, here, let's do that too. Check out, look at these sweet right angles we have going on. So, yeah, for basically a variety of reasons, in order to have a well-defined quadrilateral that has three right angles to start with, it wouldn't make any sense for CD and AB to intersect. So D has to be equal to E, and that's actually going to finish our proof, because if D has to be equal to E, well, we know that CEB is a right angle, that means CDB has to be a right angle. And so we're done. We've shown that our quadrilateral, that in a Euclidean plane, meaning a Hilbert plane in which the Euclidean parallel postulate holds, if we have a quadrilateral that has three right angles in it, the fourth angle would have to be a right angle. Yes, Don?
I understand the end of the proof, but I'm not sure how. Yeah. Yeah, I guess you just lost me. I'm not sure what's going on in that proof.
Sure. Well, let's summarize the proof again. So basically, Congruence axiom 4 tells us that since we have this other angle over here, let's say, I don't know, BAC, this right angle, that on this ray going from B in the direction of D, there has to exist a unique point that if we take the angle with C that is formed would give us a right angle. That's just kind of one of our congruence axioms. That says there should be a unique point on this ray that if we extend out to the left will give us a right angle. And if this point E happens to exist, then CE and AB are both perpendicular to the same thing. And in a Hilbert plane, lines that are perpendicular to the same line have to be parallel to each other. That was something from a previous packet. That if
CE and CV are both perpendicular?
CE and AB are both perpendicular to the same thing, namely the line here, BE or BD, whatever you want to call it. Since CE meets this line at a right angle, and AB meets this line at a right angle, that tells us CE and AB are both perpendicular to the same line, and lines perpendicular to the same line have to be parallel to each other, or the same line, which doesn't make sense here. And then CD and CE, we know CD has to be parallel to AB for reasons we were talking about earlier, because otherwise we wouldn't have had a quadrilateral to start, or as Jack said, it would have broken this Hilbert plane property that these things are both perpendicular to that, so they have to be parallel to each other.
Oh, sorry, I think I'm confused on that. So, the Sakari quadrilateral, is that the top line, is that perpendicular to?
To the sides?
Yeah.
Not necessarily. In a Sakari quadrilateral, these top two angles have to be the same, but they don't have to necessarily be right angles.
Alright.
And that was the sort of thing where we saw that in Euclidean geometry, these both have to be right angles. So yeah, I guess if we're working in a Euclidean plane, yes, those would both be right angles.
Alright.
But if we're working over a Hilbert plane where we don't have the Euclidean parallel property, then these could both be acute or they could both be obtuse.
Okay.
Hilbert plane just tells us these would have to be the same.
So because it's an Euclidean plane, D has to be perpendicular?
Correct, yeah. Yeah. In the third part of the proof, as Steph pointed out, that we didn't actually use the Euclidean parallel property at all in these first two steps. The first two steps we could have done in any Hilbert plane. But it's this third step where we needed to be in a Euclidean plane specifically to say that because CE and CD are both lines that pass through the point C and are both parallel to AB, CD and CE had to have been the exact same line.
Okay.
That you can't have multiple points, that in a Euclidean plane, it's impossible to have multiple lines passing through C that are both parallel to AB. Okay?
Maybe this is just like another way to prove it, but couldn't you, or could you just ignore the point E and just go straight to CD is perpendicular to AC, so it's parallel to AB, so it's also perpendicular to BD, so that it's a right angle?
Say that again. Give it a little slower so I can draw a picture out while you say that.
Oh, so if, angle C is a right angle, then CD has to be perpendicular to CA.
Yep.
And then that means that it's parallel to AB.
Yep, because they're both perpendicular to the
Yeah.
same thing.
And then AB is perpendicular to BD, which means that CD is also perpendicular to BD, and so that's a right angle.
So basically, CD is perpendicular to AB, AB is perpendicular to AC, so the top and bottom are parallel to each other.
Yeah, and then AB
Meets up with this at a right angle, and so if you have two parallel lines that meet up at the same thing and one meets up perpendicularly to BD, does the other have to meet up perpendicular to BD? And I would say yes, because that was one of the equivalent conditions to the Euclidean parallel property in a Hilbert plane that I think we saw at the beginning of the last packet. That if we have two parallel lines that both get intersected by a transversal, in this case BD, and if one of those parallel lines meets up with BD at a right angle, then the other one would have to as well.
Could you use that in this proof, or no?
Yeah, oh, that would be another way to prove this. That, if you do it that way, then the connection to the Euclidean parallel postulate is a little bit, it's less explicit. You're relying on some condition that's logically equivalent in a Hilbert plane to the Euclidean parallel property. Whereas this version of the proof, which is probably, I don't know, maybe about as long or maybe slightly longer than what you said, Katie. This version uses the Euclidean parallel postulate very explicitly. The fact that we can't have multiple lines passing through C that are both parallel to AB, therefore these two lines have to have been the same. But yeah, that would have been that would be another way that you could go about proving this. It's basically just this kind of pattern of perpendicular, 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 therefore parallel. Perpendicular, parallel, therefore perpendicular. Sort of idea. Yeah, no, that's a good idea, and I think that would work out as another way that you could prove this using one of our equivalent conditions to the Euclidean parallel postulate. But something that is important, though, is just because you know that if these two lines are top and bottom lines are parallel to each other, and this meets up with this line at a right angle, if we were working in something that wasn't a Euclidean plane explicitly, that wouldn't be enough to say that this is a right angle, even if we know that these two lines are parallel. Go ask some really good questions about this. Any other questions or comments? Okay, so Lamborgh Quadrilateral, fourth angle, always going to be a right angle in a Euclidean plane. So, let's give you all something to do. Small group work. I'm going to challenge you. Draw a Lamborgh Quadrilateral in S2 and a Lamborgh Quadrilateral in the Poincare disk. And see what you find ends up happening about that fourth angle.
Quadrilateral. I thought of that when you said this one. It's good stuff. Do you like it? Yeah. Wait, how do you do?
So if you recall, in the Poincare disk, that was the model we introduced on Monday, where points are always inside the unit disk and lines are either diameters of the unit disk, meaning lines that go from one point to the opposite point on the circle, or the circular arcs that intersected the outer circle at right angles. So go ahead and try and construct a Lamborgh Quadrilateral in each of these models and see what you notice.
Also swap it over here.
And then they have to point
this
over.
so they have to
I was trying to think,
Sorry, I still have a question about that curve.
possible to
Yeah.
have another seven.
So these are the three angles we have.
Correct.
And,
We're starting to assume that, we're starting by assuming that all three of those are right angles. And the question really becomes, can we prove that it also has that right angle?
This one's really weird.
So this is the Lamborgh.
This is like-
So not necessarily secondary?
Yeah, the proof I did was only for Lamborgh. It turns out for Sakiri,
It's just, he's not.
it turns out you need a slightly different proof for Sakiri quadrilaterals, and I didn't feel like it.
You're right, you can't be.
If we're starting with Sakiri, then we don't know then we would still know the line angle for right angle. We would not know that at angle C we have a right angle, but we would also know that at AC and BC are sides are angled. So we would be given slightly different information to start, and it would still have to be the case that fourth angle or in a Sakiri quadrilateral, both of the top angles are.
This one, I don't.
Oh, sorry.
This is
We know this one, right?
In a security quadrilateral, not necessarily.
Not necessarily, but in
Yes,
Also,
Lamborgh.
This is gonna be,
and then you're putting
You're right,
point
you're
E
right,
such
they,
that
they
this
can't be.
is
I
right.
feel like.
Yeah, such that the angle we get at is a right angle.
greater than
Oh,
that.
and-
We just made it.
Yeah, and congruence axiom 4
90
proves that a
degrees
point E
from there.
has to exist that makes a right angle there.
Yeah, yeah.
And then the rest of the proof is proving that that line, that point E, where you get a right angle with BP, has to just be that the only way to have a point on this line that makes a right angle with C is
No, I
just have
think I can. Look, okay, so what I'm gonna do,
Not an S2.
right, we got one right angle,
Sorry.
dub,
Why?
and then I'm gonna do
Why
a
is there
circle
going to be a
like
right angle
this.
Small.
because of
It's a right angle there,
because of
right?
congruence axiom 4. Congruence axiom 4 says that at some point on this line,
Yes, to get a right angle.
Yeah, so this.
there has to be a right angle that's formed with
This can be security, this can also be whatever. Okay.
Congruence axiom 4 says there has to be a point that makes a right angle here, and then the rest of the proof is just proving that that can't be. Have to be.
True measurement would look something like this then.
Sorry, I probably could have explained that.
Okay, I'm just gonna probably like to do it.
I don't think you can get it to cross.
I just.
I don't think
Oh,
we
wait.
should just second Diane.
I just don't think so as well.
I don't think you can go like.
What, you can't make
Listen, it
the,
won't.
Lamborgh Quadrilateral?
I don't think so. I don't know.
No, it could be.
Oh, yeah, yeah. I was gonna say, you can't make Lamborgh Quadrilateral without,
Like this is, and then these.
Yeah, I will say this, I use 2 diameters to help me construct
And
columns.
then. Okay.
2 diameters and then 2
And then this is
circular.
gonna be.
And it's going, this is looking there. And then this person is just gonna go this very way across.
I'm so bad at drawing these, and I'm not sure if it's just my drawing being flat.
No, because
It's actually like, you have to look
Yeah.
at it, you know what I mean?
It's just like if you,
For
if
sure.
you
It's
angle
like,
it
is
so
this
that
actually possible, or am I
whatever,
just trying to
whatever
make
line
this
you're
look like
looking
in a
at
circle
becomes
right now?
Yeah, there's always the issue that like, our constructions have to be logically independent when you prove things, which means if you're trying to construct counterexamples by drawing a picture, there's always some sort of, you gotta believe me, it behaves like this, I tell you.
Just trust me, bro.
Trust me, bro.
Yeah, yeah, but it's still a great circle.
I am. If you put it directly on the
But
side,
if you pick any point and go to
like what you
straight
have to do is you have
line.
to circle, like directly down the side, and it's like any circle is going, if the center of the circle is here,
There it is.
then any circle you draw within 90 degrees. Same thing on the other side, so it's big enough that they are.
if you have,
What do you mean by it
So
doesn't?
I'll draw it a little better, but
if you draw it.
I will say this, you can
that is always gonna be at its right angles.
they might not look like what you would want them to look like, but it is
There's
possible.
no such thing as squares in the plane
So
curvature.
you do this.
Yeah.
Okay, well, how about
Get a right angle from like,
Yeah.
something like going
Yeah,
here.
there is such thing
I
as
think we're gonna
squares.
get a point here and a point
Too bad.
further down.
I don't like.
That's good soup. That looks like basketball.
It does look like a bad.
All right.
But you could take like a point up here and
joke.
then
Yeah.
you're gonna go in a way that's
With angle degrees, this one's definitely 90. I went with
I got actually like recently here, like having trouble breathing. But I don't know what I did. I just kind of stretched.
Oh, okay.
Oh,
So
of course.
this one's 90.
What's it, the square dress up as?
This one is
Square dress up as for
this
Halloween.
way.
Yeah.
That's good. Hey, quadrilateral. I thought of that when you started talking today.
A security
Are you
quadrilateral.
proud of me?
So yeah, I make a right angle there, and that makes this.
I am proud of you.
Thank
Tell me
you.
when the Dr. J
That's the
was.
first time I've ever thought of a joke on my own.
This is not the first time you've ever thought of it.
No, well,
And
besides
then
Harley,
I
no
think
worse.
that's the, what you call it style, security.
Wait,
These
I
are gonna be the same.
Pulling out the screw, I see.
Yes,
Nice.
yes, you figured
I would
everything
have
out.
drawn. Hopefully, maybe the pointer, the other one's too confusing.
I'll draw the other one. I don't think we can. Literally going.
I like the quadrilateral.
Oh, yeah, yeah, no,
Stop.
No,
there's
I
definitely a
can't.
way to
Okay,
do it.
so
all.
bad.
I don't like that.
But then it's not gonna be square.
I stretched like 10 minutes ago, and I can't.
So like I can't.
So it's like, you know when it like seizes up and you like can't breathe in all the way?
All right, I have a actual question before they hear my group.
Are you asking us whether Security and Lamborgh Quadrilaterals exist?
Not really, I'll just tell you, they exist.
They do, yeah.
I'm just telling you, for this, I just wanted you to try drawing one to see what it kind of looks like. And what do you notice about the fourth angle in your Lamborgh Quadrilaterals there?
Yes. Got it.
Like not wrong, but
I forgot the question, so I wasn't
but
sure
you need to
what we
like
were
10
supposed
to
to
put pressure on
do.
before you look.
Yeah.
So now I'm not
Sorry.
anymore, but.
So they all exist.
I know, it's really hard for me.
Yeah, it really looks like they all exist.
Doing all
I
right?
said I beat the whole men's tennis team.
You're stuck on the land.
Whatever, it's the whole thing.
These sides are.
Oh, me too. I live in Germany where everyone's massive.
Wait, that doesn't
We can talk about West Poland.
This frat boys.
Yeah, like if not equal.
These
Yes.
are gonna affect a lot of
I don't know what's best for the
how
men's.
they're taken here, not us.
No, that's the
Yours is coming there too.
But I think your quadrilateral there looks fine. though.
You're all I can take.
Yeah, it'll be better.
So.
It'll be better. I hope so. for your sake.
Well, I mean, you can build a
Just,
security
you know,
on which
that
side
it's a
of
diameter,
the
you
US.
could, we're taking a right, I think this is crossing right
Oh my goodness.
Yeah, a lot of stuff.
I have some. I was about to be like,
Maybe,
you have to stop.
maybe.
It's just for you to be more.
Yeah.
You're in a geometry class, you gotta work on your drawing. Look, I'm terrible at drawing, but if you draw, I can draw what you can too.
Crazy. And it's just it's
Yeah, and you
usually
can.
right, but I was
You
really
realize
like,
yourself is not gonna hit that.
You're in the same prime. It's a great circle. Great circle.
I don't know.
So the word is actually there with the side.
So if you go in lane by Kendall's, and you turn right, you go soccer.
Whoa, yeah.
That's a good one.
That means between any two lines, there's an area. You can measure the area between lines.
Alrighty, let's come back.
They have an actual sphere.
Yeah, I was gonna say, they actually, I would say, Jared Lacey pulled out the big guns. Okay, let's come back together as a class. Would anybody like to draw out their example of a Lamborgh Quadrilateral on S2 sphere? Megan, you want to give it a go?
Do you want this one?
I was gonna say,
I'll suffer.
we do have an actual sphere there.
I'll suffer.
No thanks, I prefer to draw my spherical things on non-spherical surfaces.
Absolutely, that's just a slice of life.
You can see the whole sphere on a non-spherical surface, but on a spherical surface, you can't see the whole, like.
You can make it bigger on a big black chalkboard than on a little sphere, huh?
Well, yeah, but you also can't see the back, but you can see like through it, because it's like dotted lines.
We need to make that one see-through, like.
Like, yeah, like a clear sphere. Yeah, clear with dry erase, but that'd be awesome.
No, chalkboards are better.
But
That sounds fancy. I don't know if that's in the departmental budget, I'll have to ask Dr. Delore.
when's your birthday, Dr. Chris?
September. Am I getting a birthday? Oh gosh, am I getting a birthday present? Okay, Megan, tell us about what you found.
Again, I'm not sure if this is just my poor drawing skills or if this is actually possible, but I hope it's actually possible. I have two longitudinal lines going down, same thing we always do, right angle, blah, blah, blah. And then this is the equator, right? And you draw another great circle from the equator so that you have this right angle right here, and this is greater than 90 degrees.
Jared, I see you grimacing.
Oh, I was just wondering about the right angle from the other great circle through the equator. I think it'll be a wonkier great circle,
Yeah, I think
but you can still get the same, like, it's gonna turn out the same result though.
it's going to come out to the same result
Yeah.
either way, yeah. All right, thank you, Mike. So yeah, it's going to turn out that no matter how you draw it in S2, moral of the story is all Lamborgh quadrilaterals have a fourth angle that happens to be obtuse. How about the Poincare disk? Lane, you want to give that one a go?
Yeah. Man, I was gonna use that one.
No? Now you can't. Life can be like that sometimes.
Okay.
So, no, you even want to make your third right angle inside the quadrilateral. You could make it outside.
Okay, so we have two diameters crossing at a right angle, and then you can construct these two circular arcs so that they cross each diameter at a right angle, but then they're going to intersect each other at a less than 90-degree angle.
Oh, ain't that a cutie?
Okay.
Questions for Lane about her drawing? All right, nice job. So, anyone want to take a stab as to guess what all of the fourth Lambert quadrilateral angles are going to look like in the Poincare disk?
Oh, less than 90 degrees.
They're all acute. Yeah, so in this model, all Lambert quadrilaterals have an acute, meaning less than 90 degrees, fourth angle. So yeah, so we've seen something interesting. We've seen that triangles and Lambert quadrilaterals both have some interesting properties to them in Poincare disk versus spherical geometry. In spherical geometry, the fourth angle in a Lambert quadrilateral has to be obtuse. We've also seen that the summit angles in a Saccari quadrilateral have to be obtuse. That's interesting. In the Poincare disk, we've seen that the fourth angle in any Lambert quadrilateral is acute. We've also seen that the summit angles in any Saccari quadrilateral are also acute. Coincidence? Technically, yes, because these are not Hilbert planes. But as it turns out, if we flip the page, we got a nice theorem that tells us something about how we have a couple of theorems that actually kind of give us a nice relationship here. So it's going to turn out to be the case. So the uniformity theorem. So first of all, the uniformity theorem basically is just going to say that if any Saccari quadrilateral has acute right or obtuse summit angles, then every other one has to as well. Meaning if you're in a Hilbert plane, and you can find one Saccari quadrilateral whose summit angles are both, say, acute, or they're obtuse, or they're right, then every other Saccari quadrilateral in that model is also going to have the same type of summit angles. Note that that doesn't necessarily mean the angles in any two Saccari quadrilaterals have to be congruent. It could be the case that in one Saccari quadrilateral, you get summit angles that look like this, that are obtuse, and in another one, you get angles that are super obtuse. So, in other words, the summit angles in any two secondary quadrilaterals don't necessarily have to be the exact same, but if you have obtuse summit angles in one secondary quadrilateral, in any other secondary quadrilateral, they're also going to have to be obtuse. Dr. Gerstel, what kind of right angles are you trying to draw here? Shut up. I'm trying to illustrate a point that's hard, okay, on a chalkboard. Unless I want to really carefully draw these out in painstaking detail, it'll take like 5 minutes for it. Same is true for the fourth angle in the Lamborgh Quadrilateral. According to the Uniformity Theorem, that if you know one Lamborgh Quadrilateral has a fourth angle that's acute, then every other one does too, and ditto with right and obtuse, though just because they have two acute, just because they all have to be, say, acute, doesn't mean they're all congruent. And then it turns out that the summit angle type of secondary quadrilaterals are going to be the same angle type as the fourth angle in every Lamborgh quadrilateral. Basically saying, if your secondary quadrilaterals in your Hilbert plane all have obtuse summit angles, then the fourth angle is also going to be obtuse in any Lamborgh quadrilateral. So if, for instance, S2 happened to be a Hilbert plane, which it isn't, then the fact that it's possible to have one Lamborgh quadrilateral with an obtuse fourth angle means that not only every other Lamborgh quadrilateral would have an obtuse fourth angle, but it would also mean that any Sakari quadrilateral has to have summit angles that are obtuse. And ditto for the Poincare disk, replace the word obtuse with acute. Since one Sakari quadrilateral in the Poincare disk has has acute summit angles, all the other Sakari quadrilaterals have to have acute summit angles as well, and that would also imply that the fourth angle in any Lamborgh quadrilateral would have to be acute. So, in other words, the missing angles are either all going to be acute, they're all going to be obtuse, or they're all going to be right, depending on the model that you're looking at. Questions or comments about that? And here's another gnarly result. If you remember, in spherical geometry, we said that any triangle that you draw is going to have triangle sum greater than 180 degrees. And in the Poincare disk, any triangle you draw is going to have an angle sum less than 180 degrees. Turns out, if you look at Sakari's angle theorem part 2, that's actually going to be heavily related to the missing angles in Sakari and Lamborgh quadrilaterals. In that the angle type of the summit angles in a Sakari quadrilateral is acute if and only if every triangle's angle sum is less than 180 degrees. The missing angles are in the quadrilaterals are going to be right angles if and only if every triangle has an angle sum exactly 180 degrees. And it's going to be obtuse if and only if your triangle angle sums come out to greater than 180 degrees. So this sort of connects the behavior of triangles and quadrilaterals in your models in the sense that if you know something about triangle angle sums in your models, that tells you about how Lambert and Sakari quadrilaterals behave, and vice versa. If you know what the missing angle types are in your Sakari and Lambert quadrilaterals, it tells you what your triangle angle sums in your model should come out to. Check out this lovely looking quadrilateral. There, that's now one side.
Okay.
Any questions or comments about either one of these theorems? We're not proving either. These are not easy things to prove. But they are interesting results, I think. Basically saying how do triangles and quadrilaterals sort of relate to each other? And I'll give you a hint how you would prove these. Side angle side. here. That's my hint.
Does this, it seems like we're consistently dividing all geometric models up into like 3 different ones based off of like the degree of an angle. Does this like continue for like a bunch of different polygons and other stuff?
You can generalize and say some result about, oh, if the triangle angle sums less than 180 degrees, then that tells you something about the quadrilaterals, which would also tell you something about pentagons, for instance. Like, if you know the angle measurements of these 4 pentagons, then the last one will have to behave like this somehow. And I don't think we're not gonna extend this theorem this result any further in this class, but you can generalize to polygons with more than 4 sides as well, depending on your model. All right, that's gonna do it for today. When we come back, we're gonna talk about semi-Euclidean planes. And Aristotle's angle unboundedness axiom. That's right. Why is Aristotle? This is a Hillsdale class. I feel like I'm going to get fired if I don't talk about Aristotle at some point.
I'm gonna quit this class. 2 weeks left.